Alright, so I think this is recording. Someone asked me to make a video of the solutions for this homework assignment, or actually a couple people did, um, because maybe it's the reasoning behind that might be that it's been so long since they've looked at synthetic division that maybe that's it. With this remainder theorem, see, before the remainder theorem, if they were asking us to evaluate this function at -5, we would simply plug in -5 everywhere we see an x. So I would get out a calculator. I would not do this by hand, but it's possible that maybe you want to do it by hand just to gain confidence in the theorem. I'll leave that up to you. I'll write it out for you. Well, so if I've copied this down correctly and not made a mistake copying the exponents, this is a lot to write out, so it's possible to accidentally make a silly error. I claim that you can do that on a calculator. Do it by hand if you'd like. There's an easier way that I would do it by hand, and that's using this remainder theorem. They're wanting me to evaluate this at -5. Well, I can do synthetic division with my 0 being -5. For synthetic division, I need the expression to be in standard form. So the exponents need to be in descending order, and it is. And if I have any missing exponents, I would use a 0 as a placeholder for that term. But I have an x to the 7th. I'm just using the coefficients 3, 12, -14, 7, 10, 2, 8. All right, now, you always bring down the first number below the line. And then if that number is below the line, it gets multiplied by this number in the box. Then you start writing from left to right. So I add this together and I get a -3. I multiply the -5 times the -3 and get a +15. I add and get a 1. So then again, I'm below the line, so I multiply. Then I add. I'm below the line, so then I multiply. Then I add. Then I multiply. Then I add. And I get here a -2. Now, that -2 is the remainder for this division problem. Remember, synthetic division problem is a division. The synthetic division just allows us to do it in a compact form, just using these coefficients. So I claim now that if you were to take a calculator to do all this arithmetic, you're going to get -2. That f evaluated at -5, which is what they want us to answer, hey, it's -2. Okay. I don't know what -5 raised to the 7th power, but down here, the arithmetic was such that even I didn't need a calculator. So when you have big exponents and fairly large numbers, this synthetic division provides you an alternate way to evaluate functions at specific values. So I'm going to move on and do these maybe in one video. I'm running close for time tonight, so normally I try to split up and do the problems a problem at a time, but this would be a long video because I'm just going to do it all at once. Alright, so it's the same idea here. So let's check, is this in standard form? 6, 5, 4, 3, 2, 1, and then the constant term. It's in standard form and I'm not missing any terms. So rather than plug in 2 and have 2 to the 6th power and replace x with 2 everywhere, I'm just going to do this synthetic division. So remember, there's a 1 in front of there, a -4, a 6, a -3, a 3, and -6. If you had time, like if it was homework, I'd probably go ahead and plug in 2 just to double check my answer. And if it was a quiz or a test, it would just be depending how much time I have at the end whether to check the answer or not. So the first number always comes straight down. And then if you're below the line, you get multiplied by that number that's in the box up there. 2 times 1 is 2. Then I add. Then 2 times -2 is -4, and I add. And 2 times 2 is 4, and I add. 2 times 1 is 2, and I add. And then I multiply, and then I add, and then I multiply and add. So that's my remainder. So I claim that f evaluated at 2 is equal to 7. If you provided I haven't made any silly arithmetic errors, if you're wanting to check that answer, plug in 2, evaluate 2, this function at x equals 2, and see if that arithmetic doesn't produce that, an output of 7. Same direction, same idea. Now, let's check and see if this is in standard form, because just because the others were doesn't, they do that a lot to you. They give to you standard form, this whole list. All of a sudden, when you don't think to check, boom, they give you one that's not in standard form. 4, 3, 2, 1, 0, it's in standard form. -8, 1, 2, -30, 150, that's kind of big. I might have to use a calculator for this one. All right, the 1 comes straight down. I multiply it by -8. I multiply it, then I add, then I multiply, I better check. For a math teacher, I am terrible at mental arithmetic. Yeah, -144. I just, for some reason, didn't recognize that. Alright. So, hopefully you won't tell me tomorrow that I made a silly arithmetic error. Yeah. I claim, if I haven't made an error here, that if you evaluate this function, if you replace x with -8, that you'll get -26. If you do not, then either check and see if you've keyed it in the calculator right. Remember to put parentheses when you have a negative input. If you have -8 raised to the 4th power and you keyed in like that, that's not the same thing as parentheses. This on the right is a positive number, on the left is a negative number. They're not equal to each other. So the parentheses are important when you're using the calculator and keying it in to check your answer. And then just try to double check and make sure that you haven't made a silly arithmetic with pencil and paper. Now here, this time, we take it a step further. Notice that they're saying that when you evaluate this function at -4, you get 0. And by that second theorem we had in the skill packet, that factor theorem, if you have this evaluated, the function evaluated at -4 equals 0, says that we can write now a factor of this polynomial. Now we have to change the sign. That if the x-intercept is -4, in factored form we write it as x plus 4. But it wants us to show, so it wants us to verify with synthetic division, and this is in standard form 3, 2, 1, 0, that we have a remainder of 0. And I get it. If I didn't get a 0 there, then either I've made a mistake or they've made a mistake in their a typo in their in their statement. So I'm positive now that f evaluated at -4 is 0, and I'm also positive now that this function that was a third degree polynomial, that I didn't have any X method or any technique to factor this, but since they gave me this piece of information, I know now that I can factor this to x plus 4 and use this result from the synthetic division of x squared plus 2x minus 1. This one was 1x squared there. All right. Now, it says to use the result to find all of the factors. So it's not necessarily asking for the x-intercepts or the zeros, and I think some people went ahead after they factored it and solved the equation. It's not asking me to replace this with 0. It's just saying factor this completely and present the factors. So I've got x plus 4, and this guy factors to x minus 1 quantity squared. It's a perfect square. No, it's not. I have to use the quadratic formula. That's not a perfect square. Sorry about that. So the opposite of b is -2 plus or minus the square root. B squared is 4 minus 4 times a times c, all divided by 2a. And so this guy, well, what am I doing? I sit there and say, I'm stupid. I'm finding the x-intercepts. I'm finding the zeros. It didn't say find the zeros. It just said find the factors. Well, sometimes you'll have an expression that you can factor and sometimes you can't. So I found the factors. They're right here. I'm so used to the fact that why do we have this in factored form? We do it to set it equal to 0 to solve this equation. And then this x squared plus 2x minus 1, since it didn't factor any further, I have to use the quadratic formula. It did not ask me to do all this work, so why was I doing it? I don't know. So that would be a quadratic formula. In the future and stuff, most of the time it does ask us to do that. Sorry about that. I don't mean to waste your time. All right, so it wants me to show that this is equal to 0. So with synthetic division, this is in standard form. There's no missing terms. I have a 1 there, -8, 9, 18. Since this is 0, I'm expecting this remainder to be 0. If it's not, then something's wrong somewhere. And it is, well, what that allows me to do is to factor this f of x. We know that we have this x cubed minus 8x squared plus 9x plus 18. And now with this piece of information and the synthetic division, I know that I can factor this to x minus 6 because the 6 minus 6 gives me a 0. And then here, if you go in the reverse order, this is your remainder. That's your constant term, your x to the first, your x to the second. So I've got 1x squared minus 2x minus 3. And now I look and see, hey, can I factor this? Well, last time I couldn't, but this time I can. Or at least at first glance, I think that I can. To factor it to x minus 3 and x plus 1, right? See, last time I couldn't factor that, so I was allowed to stop right there because all it wants is the factors. This time I didn't want to stop there because I can continue. It does want me to factor it completely. So there's my answer for number 5. All right, I want to show this, so I guess maybe we have some doubt that if I get a remainder of 0, is this in standard form, and make sure I don't have any missing terms. 3, 2, 1 constant. It's in standard form with no missing terms. You know there's going to be some point where we have a function here that's not in standard form or that has missing terms that we need to fill in a 0 there in order to line the columns up correctly. So hey, I get a 0 here. So I'm pretty confident that I have done this correctly. I suppose I could have gotten, well, unlucky and gotten a 0 and did it incorrectly because I need this 2, 7, and 6, right? This function that is given to me as 2x cubed plus 21x squared plus 55x, I don't have any techniques yet that allows me to jump in and factor this third degree polynomial. But with this added information that they gave me and my knowledge of that remainder theorem and factor theorem, I'm able to argue that this factors to x plus 7, because in factored form you change the sign, and then here I have 2x squared plus 7x plus 6. Now we saw in that previous problem, sometimes I'll be able to factor this, other times I will not be able to factor it. All they want this time is the factor, so I don't have to set this equal to 0 and solve it. So let's spend a little bit of effort and see, can we factor this? Well, if we can, this first term, 2x times x is 2x squared. I need two numbers that multiply together to give me the 6 there. So either 2 and 3 or 6 and 1. I need it to add up to 7. So what if I use plus 3 and plus 2 here? Well, the 2 times 2 gives me 4, and 4 plus 3, hey, that gives me 7. So now, most of the time the people in the pre-AP can factor that just by looking at it. However, you know, there are maybe some people that still like using that X method that you learned if you took Algebra 1 here rather than over at North Clay. So the Algebra 1 team says that if you have this 2x squared plus 7x plus 6, it's a difficult factoring problem when you have a leading coefficient that's different than 1. Now we're lucky that that's prime, because if that had a lot of a composite number with a lot of different factors, it's a little bit harder to just do it in your head. So the first term times the last term is 12x squared. Two numbers that multiply together to give me the 12x squared but add to give me 7x are 4x and 3x. When this is different than 1, they suggest that you create a table, and in one diagonal of the table you write the first term and last term of the original expression that you're trying to factor. So it's always this first term and last term along one diagonal, and then along the other diagonal are the numbers that we found through trial and error in that X method. Because see, we had to think about it for a minute. What if it was 1 and 12 or 6 and 2 rather than 4 and 3 that worked there? So it doesn't matter when I write 4x and 3x how I put it along the diagonal. I could have written 3x here and 4x up there. Now I factor both horizontally and vertically. When I look across here, 4x and 6 are both even numbers. They have a 2 in common. When I look vertically here, both of these have a 3 in common, and 2 times 3 gives me 6, so I haven't made a silly mistake. When I go across here, the numbers 2 and 3 are relatively prime. They don't have a common factor, but both of these have an x in common. And since that's a 1x, here I need a 2x squared, so this will be 2x here. And look, an x is common, and they're both even numbers. So I'm pretty confident. Look here, I've got 2x plus 3. Well, there's my 2x plus 3. X plus 2. Well, there's my x plus 2. So I'm pretty confident now that I did that correctly. But some of you, there's no shame in using that X method. I have to use it quite frequently, especially when this number has a lot of different factors. If that was a 12 or a 24 or a 36, my goodness, I'm going to definitely have to use this method or some organized method to factor it, because in my head there'll just be too many combinations to go through that I just might not find. All right. Again, they're just wanting the factors, not necessarily the x-intercepts, which are also called zeros of the function. So now this time they give me the information, they give me a factor. So when I go to do my synthetic division, 3 minus 3, I need the 0. 3 minus 3 gives me 0. I have to change the sign of that. Is this in standard form? And are there any missing terms? Well, 4, 3, 2, 1. I can put plus 0 for a constant. Otherwise, I might get the remainder. I might be confused there on the remainder. So I am going to add a 0 on my synthetic division. So I've got 1, -3, -1, 3, and 0. The 1 comes down, gets multiplied by 3. I add, I multiply, I add here. And 3 times 0, hey, that's 0 and that's 0. So I might have gotten lucky if I hadn't noticed that and thought the remainder is 0, but really I needed that in there. So what does that do for me? Well, that helps me factor this at least part of the way. This x to the 4th minus 3x cubed minus x squared plus 3x. Now, I don't need synthetic division to look and notice that an x was common everywhere. So yeah, maybe that's would have been smarter to have done first, and then I wouldn't have had to have worried that. So, just because I'm relying on synthetic division as a new idea to help me factor, I don't have to lose my old ideas of easily recognizing that all these terms have an x in common. So it probably would have been smarter to have written x and then x cubed minus 3x squared minus x plus 3. And then when I use these numbers, I wouldn't have had to have worried about that last column right there, right? I've got 1, -3, -1, and positive 3, and this is a 0 right there. So I found this factor of x on my own just using the common methods of just recognizing it was the greatest common factor. Then by the fact they gave me x, they gave me a factor. They said x minus 3 is a factor, so let's come down and use that. I found that x was a factor. They told me that x minus 3 is a factor. Using synthetic division, I'll find the other factor. Well, this was the constant. This is the linear term, minus 1. There is 0x to the 1. So this guy, let's write it over on the side. This is 1x squared plus 0x minus 1. Well, we're not going to write the 0x in there. We're just going to write x squared minus 1. So we can factor that. We've seen that plenty of times, that's the difference of perfect squares. That you've got x minus 1 times x plus 1. So now we took this 4th degree polynomial and factored it completely. We used the fact that they gave us one of the factors, but we found the other factors on our own. One of them just through traditional methods of greatest common factor, and the other with this synthetic division that relied on this remainder theorem and zero factor theorem. So here I have a 5th degree polynomial, but they're telling me that I have one of the factors, and it's asking me to find all of the factors. So and it's wanting me to show that that's true, not to just blindly believe them. So I'm going to do synthetic division, and I should have a remainder of 0 if what they're telling me is true. Now, is this in standard form? We've got 5, 4, 3, 2, 1, 0. And this time, I don't have any common factors. I'm not going to make that silly mistake that I did last time. I need to look and check, is there a greatest common factor? Because that's what I'm really wanting to do is factor it completely. So I apologize. I should have thought of that on that previous problem looked for that greatest common factor first. So the 1 comes down. Now I multiply by the number in the box, and I add, and I multiply, and I add. And if I'm not making any silly mistakes here, and hey, I get a 0 there. So that makes me pretty happy. So what this does for me is this 5th degree polynomial. I guess by now I don't have to rewrite it, but I just am doing that out of habit to illustrate to you guys how am I getting this second step here. Well, I'm getting this next step by two things. One, they've given me x plus 4. And two, I know now through the synthetic division that if this is 1x to the 4th, I don't have any x cubes minus 5x squared. I don't have any x's plus 4. Okay. If you multiply these together, that's what you're going to get. Now, although there were zeros here, it's awkward for me to try to factor this with those zeros there. So I'm going to write this again without those 0 terms. So I've got x to the 4th, and then look at this middle term. Its exponent is half of that leading term. So this is, they say this is quadratic, even though it's to the 4th power. It's quadratic in x, that we can factor this as a product of quadratics. So to get x to the 4th, I have x squared times x squared. To get the 4, well, I also need both of the values to be negative, because the negative times negative is positive, but that middle term is negative. So I either need a -1 and a -4, or a -2 and a -2. Well, what works is a -1 and a -4. And that's also nice because, hey, that's a difference of perfect squares. That allows me to keep factoring it. So it's kind of nice that it wasn't x squared minus 2 times x squared minus 2, because this is easier to factor. I've got x plus 4, x plus 1, x minus 1, x plus 2, x minus 2. Now, I don't have any common factor. If we see any factors that are listed more than once, we would want to combine them and change the exponent. But I don't see another x plus 4 factor. I don't see another x plus 1 factor. So this is my final answer for problem number 8. All right, number 9. So 3, 2, 1, 0. This is in standard form. They're giving me one of the factors and they want me to show that that is a factor. They're not saying to blindly believe them. So the x minus 2 is in factored form, which means the 0, the x-intercept, 2 minus 2 gives you 0. So I need to change the sign when I do my synthetic division. That's easy to accidentally forget to do that. But you'll be able to catch yourself, because if you don't get a 0 remainder at this point, then something's up. Look at that, we get a 0 remainder. So this function f of x that was a third degree polynomial, we know one of the factors is x minus 2, and the other factor is 6x squared plus 13x minus 5. Okay, so the question is, well, is it possible to factor this? And maybe we should use that x method, because this leading coefficient is a composite number. It has factors of 1 and 6, but also of 2 and 3. So let's go ahead and use that X method, although some of you are good enough at mental arithmetic that you'll be able to look at it and maybe see whether you can factor it or not. I can't always see it, but that's because mental arithmetic is truly a weakness for me. Two numbers that multiply together to give me negative 30x squared, but add, well, 15x and minus 2x do the trick. So since my leading coefficient was not 1, I'm going to make a table. My first term and last term are along one diagonal of the table, and the values I found in my x I can put on the other diagonal of my table. I look horizontally and I see that a 5 is common to both of those. I look vertically here and say, well, the numbers aren't common. There's not an x, but the negative sign is, so I'm just going to say that negative 1 is common to both. And a positive 5 times a negative 1 is negative 5, so hey, that works out for me pretty well. I look here and see that these are both even and they both have an x, so I'm going to write a 2x, and a positive 2x times a negative 1 is negative 2x. I look vertically here, 6 and 15 share a common factor of 3, and these have a factor of x, and 2x times 3x is 6x squared. So hey, I've done it. I may not have looked at this and recognized, because like I say, at first glance, how did we know it was going to be 2x times 3x? It could have been 6x times 1x. So if you're good at doing just the combinations, the possibilities in your head, then certainly do that because it's a time saver. But if you need to be organized, and if you're not good at doing it quickly and efficiently, or especially if this value is a big number, 12, 24, 36, I would suggest that you do it with this X method in this table. So we've have factored it down to linear factors, and we don't have any of these bases that are repeated there. So that's our answer. Hey, I think that's the last one. Yeah. So hey, I hope that helps, and I will talk to you tomorrow. If you need more things from me, more examples, more videos, let me know, and I will try to do it as time permits. There's only so many hours in the day, and I'm sure this video was too long, so sorry about that.